Okay, yeah, so you can find me, Jake VDP, pretty much anywhere. And I've had a really, over the last 10 years, working with Python and working with things, I've had this really well-planned career path that's taken me a few different places. I've started out studying physics, then got into studying astronomy. That led me to data science because it turns out astronomy has a lot of data, and we had to figure out how to make use of that in Python. And then eventually that led me into software engineering, and now I work full-time as a software engineer. And funny thing, I don't even write that much Python anymore. It's mostly JavaScript these days, unfortunately. But yeah, so it's been kind of a funny journey. If you look online, you'll find a few of the things that I've done. I've contributed a lot to the kind of the PyData stack, SciPy, Scikit-Learn, AstroPy, and along the way had the opportunity to write a couple books. So if you really like astronomy and astrophysics, this is a great textbook. You should check it out. And if you like, if you want to check out Python and data science, I have this O'Reilly book that's pretty fun. But anyway, so one thing that I've noticed over the course of the last 10 years working in this space is that there are a ton of questions about why Python is the way it is. Why are there so many visualization libraries? Why is it that sometimes things feel a little bit disjointed, right? You have packages that may work together, may not work together, and there are all these questions that come up, and in my hope in this talk today is I want to give you a little bit of perspective about why the PyData space is the way it is, some sort of history on how we got to where we are now, and then I'm hoping to give you a survey of kind of the general tools that are out there, so that if you have a question about how to do a certain thing in Python, hopefully one of these packages that I talk about will help you do that. So yeah, the two parts of the talk. Why is the PyData world the way it is? And what is the best tool for my job? So let's dig in. One thing to notice or to realize straight off is that Python is not a data science language. It wasn't developed as a data science language. And the fact that we're here in a PyData session talking about data science in Python comes from kind of this long history of what happened since the beginning of Python. So Python was started by this guy, Guido van Rossum, in the 80s, and he was a professor at I forget exactly where, but it was an institution where he was teaching computer science, and he decided to develop this language to help teach computer science more effectively. And so Python was started as this sort of teaching tool. And I think this is one of the reasons that Python is so easy to learn and so fun to use, is because it was created with beginners, with kind of not very sophisticated people in mind. And that means that it's really easy to express things in Python. It's very easy to transfer things from your mind onto the screen and into the code. So he created it as a teaching language and also to bridge the gap between the shell and C. So in order to keep you from writing bash scripts all the time. And it's interesting to look back and read some of the interviews with Guido and hear what he thought Python would be at that point. He said, I thought we'd write small Python programs, maybe 10 lines, maybe 50, maybe 500 lines, and 500 lines would be a big one. And now you hear from companies like Netflix that are built on Python, and you have million-line code bases, millions of lines of code all in Python. It's a totally different world than he envisioned. So what happened? How did we go from this this kind of small teaching scripting language that Guido created 30 or 40 years ago, and how did it become such a data science powerhouse? So I like to kind of organize my thinking about the Python history in terms of decades. So in the 90s or so, I think of Python as being in the scripting era. And if there's a motto in the scripting era, it's Python is an alternative to Bash. So Guido didn't want to write Bash scripts to run all the things on his computer. He wanted a nicer language to express these little scripts he was writing. And so it's interesting if you look at this, what was going on in the 90s in terms of scientific computing in Python. There's a guy named David Beasley, who you might know from if you've followed the PyCon talks, and he's a pretty prolific author. But he said from that time period, he said, scientists work with a wide variety of systems ranging from simulation codes, data analysis packages, databases, visualization tools, homegrown software, each of which presents the user with a different set of interfaces and file formats. And as a result, scientists may spend a considerable amount of time simply trying to get all these components to work together in some manner. And Dave really was one of the people who kind of pioneered the use of Python as a glue language to take all these disparate scientific workflows and put them together in a way that made sense. And one of the tools that he created back in the 90s that's still used today is this thing called SWIG, the Simplified Wrapper and Interface Generator. And what this did is it allowed you to create kind of sensical Python interfaces to all the scientific libraries that were written in Fortran and C and other languages. And if you look at the early PyData tools, things like Numpy and SciPy, and even Scikit-Learn, they were all built on this SWIG project. They've moved on to other tools since then, but I want to make sure that we recognize kind of how useful this work was in getting us eventually to where we are today. So that was the scripting area. In the 90s, Python alternative to Bash. In the 2000s, I like to think about this as the SciPy era. And if there's a motto for the SciPy era, it's Python as an alternative to MATLAB. So a lot of folks in the 2000s who came to start using Python and get into the Python open source world were converts from MATLAB. And if you're not familiar, MATLAB is this proprietary software. You pay a license fee for it, but it allows you to do all sorts of interesting kind of scientific computing, matrix algebra, visualization type of things. And it was in the 2000s that folks started to look at this ecosystem and say, Python could be a free replacement for this and kind of let more people have access to these kinds of tools. So one guy who was really influential in this was John Hunter. He passed away about 6 years ago, unfortunately. But he was the creator of Matplotlib. And if you look at, he gave this keynote shortly before his passing in 2012, and talking about why he developed Matplotlib. And he looks back and he says, I had a hodgepodge of work processes. I would have Perl scripts that called C++ numerical routines that would dump data files. I'd load them into MATLAB to plot them. And after a while, I got tired of MATLAB, so I started using GNUplot instead. So he motivated kind of this smattering of different tools, similar to what the problem that Dave Beasley was solving in the 90s. And he decided to create Matplotlib to address parts of that. Another guy who was really influential in this time period and still now is Travis Oliphant. And he was the creator of Numpy and SciPy. And if you look at what he was doing, he was saying, prior to Python, I was using Perl, and then MATLAB, and then shell scripts, and Fortran, and C++ libraries. And when I discovered Python, I really liked the language, but it was very nascent and lacked a lot of libraries. I felt like I could add value to the world by connecting low-level libraries to high-level usage in Python. So same kind of story, a smattering of scientific tools, and he saw Python as this sort of unifying force. And another person who you might know, this is Fernando Perez. He actually grew up here in Colombia, and I think he was a keynote speaker last year or year before. But anyway, he's the creator of IPython and Jupyter. And he told me that I remember looking at my desk and seeing all the books on languages I had. I literally had a stack with books on C, C++, Unix, Oxed, SH, Perl, IDL manuals, Mathematica book, Make printouts. And he said, I realized I was probably spending more time switching between languages than getting anything done. So these three folks who created the big tools, Matplotlib, SciPy, NumPy, IPython, the problem they were trying to solve is the fact that they needed to switch contexts all the time, switch between languages, switch between different systems, and they saw Python as a way to unify this all together. So if you look at the software development during that time, these are I dug out the early logos of these projects. I love this kind of like mustard and ketchup Matplotlib logo. But yeah, so Matplotlib was released around 2002, SciPy around 2000, the original IPython interpreter around 2001, and there was Numeric and NumArray that were the early kind of array computing libraries. And actually, originally, the interesting thing is each of these folks, John and Travis and Fernando, and the people working with them, were initially trying to kind of solve all the problems themselves. Matplotlib, if you look early on, the early versions of Matplotlib actually have some computational spectral analysis things and a shell script. It was trying to replace MATLAB completely. And similarly with SciPy, the early versions of SciPy had some visualization libraries in them. And the early versions of IPython had a little bit of these as well. So they were all trying to check every box. And one of the really important things in this era is, around 2002, 2003, 2004, these three folks, as well as all the other people working with them and working on similar tools, started talking and realized that they didn't need to overlap. And so they evolved, and eventually the libraries came to be what we know now, kind of in filling their one little niche in the system. And NumPy was this unified array library that kind of underpinned all of them. So it's really, it's interesting. This is one of the reasons that Python sometimes, the PyData world sometimes doesn't feel like it's very focused. It doesn't feel like, it doesn't feel homogeneous, and that's because you have all these different people working on different things, solving their own problems that eventually come together and figure out how to work together. And I think in this case, it served the community really well to get to this point. So the big conference series, I think, in the SciPy era is this Sify Conference, which you may have been to, and there are various iterations on that. But this started out as the meeting where these developers got together, where a dozen people got together and talked about how to make these tools work together. And it's come to the point now where I think the SciPy Conference in the US attracts 600 or 800 people, and it's mostly users of this system now, which is kind of an interesting evolution. Okay, so we have the scripting era, we have the SciPy era, and I like to think of the 2010s as the PyData era. So if there's a motto for the PyData era, it would be Python as an alternative to R, right? So yeah, if you look at where this kicked off, I think I would really mark Wes McKinney's work on pandas and his book Python for Data Analysis as sort of the beginning of the PyData era. And it's interesting to look at his motivations for creating pandas. He says in the foreword of his book, he says, I had a distinct set of requirements that were not well addressed by any single tool at my disposal. Data structures with labeled axes, integrated time series functionality, arithmetic operations and reductions, flexible handling of missing data, merge and other relational operations. And I wanted to be able to do all these things in one place. Are you sensing the theme here? Everyone wants to do things in one place. All these things in one place, preferably in a language well suited to general purpose software development. And this is why he created pandas. He was using R for a lot of these things, using Python for other things, and sort of saw a need for Python to be able to do some of these more labeled data, relational algebra type routines in a way that made sense. And so he created the Pandas package. And some other key software development in this time period was, so I mentioned pandas with labeled data. The Scikit-Learn project was started around 2007, but really the development kicked off in earnest around 2009, 2010. The Conda package, this has been really important in terms of packaging up the types of software requirements that you need and installing them in an easy way. The IPython notebook in 2012 was kind of the first really comprehensive interactive environment for using all of these tools, and then that later grew into the Jupyter project, which was renamed to basically recognize the fact that it was more than just Python now. You can use Jupyter to run R, to run Python, to run Julia, to run C, C++. There's dozens and dozens of language kernels. So this is kind of the key software that I think has driven the PyData era, as I like to think about it. And the key conference series is all the PyData conference, and it's been incredible to see this grow from this little meetup that happened, I think, in 2012, all the way to this international conference series, and I think we even got us right here, so that's good. So the PyData and NumFocus has been really instrumental in sort of spreading the training of how to use all these tools effectively, and it's been a really incredible thing to watch. I've seen all these things pop up, and it's really great. So we have these three eras: the 90s, the scripting era, where they're trying to use Python as a unifying tool to prevent having to jump into Bash all the time. The SciPy era, Python as an alternative to MATLAB, as a glue to pull together all these scientific tools people were using. And then the PyData era, kind of Python as an alternative to R to bring together all the data science type workflows into the Python world. So the overall point that I want to make here with this history is people generally want to use Python. Python started as this teaching language, this really beautiful executable pseudocode. And people want to use Python for all these disparate workflows that they were using other tools for. And so because of that, what's gone on over the course of the last 2+ decades is people have built Python packages that incorporate lessons from these other tools. They build Python packages that incorporate lessons from MATLAB, from Mathematica, from R, from Bash, from Perl, from all these other languages, and you end up with kind of a unified way of doing these different things. So that's kind of how we got where we are. Python is not a data science language originally, but it's become this data science language through the effort of so many people who have built free tools to make sure Python can work in these spaces. So it's really incredible, kind of the amount of community effort that everything that we do here in a conference like this is built on top of. So remember this: Python's a general purpose language, and I think this is one of its great strengths for data science, because you can do these very specific machine learning or deep learning or data analysis workflows, but you can also go beyond that and do many other things without leaving the same language. So I like to think of Python as a Swiss Army knife. You have a little one thing. Did you mention Swiss Army knife in your keynote? I think so. That was good. But it's more than just a Swiss Army knife. It's kind of more like this. There's so much out there. There's so many tools that people have been developing. And the problem with a Swiss Army knife that looks like this is you spend 10 minutes trying to find the right tool before you can actually use it, right? So I think the space that we're in now, the weakness of Python these days is there's just so much out there, and it's hard to know where to start sometimes. So in the second half of my talk, what I'm hoping to do is sort of give you a tour of this PyData world and kind of zero in on a few places that you should look at and start if you don't know where to start for various things. And a lot of this is going to be really quick. I only have 1 or 2 slides on each individual library, but I'm hoping that just kind of with this high-level preview, you'll be able to dig in a little more and see and find more on your own, or find more through the other sessions in this conference. So the first thing you need to do when you're using Python is install things, right? And for the past few years, I've recommended Conda as a way to install Python and the PyData stack. So Conda is this cross-platform package manager. You can think of it, if you're used to Linux, you can think of Conda as sort of an apt or a yum package manager, except it's cross-platform. It works on Windows and Mac and Linux. And what it lets you do is take all these complicated compiled dependencies and install them very easily on your system. And I think people who have just gotten into the PyData system recently don't realize how revolutionary this was. Did anyone try to compile and install SciPy circa like 2009? Yeah, it was a painful experience. And Conda really changed this. So it's hard to I just want to put that in perspective, how important this tool was. And there's two flavors of Conda. There's mini Conda, which is basically like just Python plus the Conda installer. And there's Anaconda, which is mini Conda plus hundreds of packages that the creators of Anaconda think you would find useful. So you can decide whether you want to go the minimal route and then just install packages as you need them, or if you want to go the full route and just get the whole ecosystem on your computer at once. So I usually recommend starting with mini Conda because it's a little bit lighter. You can go to this download page and install whichever system, whichever operating system you need. So once you have the mini Conda download, you can install it this way, and you get this new command line tool called Conda. And if you look at your Python, once you've installed that, you can see that the Python you're using is sort of in this Anaconda directory. So basically, what Conda does is it sandboxes your Python environment. It doesn't use your system Python, because modifying your system Python can sometimes cause problems. You get this sort of sandbox data science development environment. And you can run Python, you can write code, and then most importantly, you can start installing the packages that you want. If you type conda install, Numpy, Scipy, Pandas, Matplotlib, Jupyter, whatever you'd like to install, those are there, and it will set them up correctly configured for your system. So the other thing that's nice about Conda is you can create environments that have different versions of Python, different versions of packages, using this conda create command. Conda create, that -n means the name of the environment, and then you tell it what packages you want and what versions. And for me, this has been really helpful in my development workflow, because often when I'm contributing code to SciPy or to AstroPy or to some other package or working on my own research, you need a different set of packages. And the ability to install and switch between these environments very seamlessly and try things in different versions of Python is really helpful. So once you've created that environment, you can activate the environment. And you can see that the Python version is now 2.7 since we did a 2.7 environment. This sort of thing is going to get less and less relevant because Python 2.7 is going away soon. But it's the ability of Conda to create these environments is really useful. So I have a ton of environments. I have development environments. I have different versions of Python and things like that. And you end up with that if you use Conda for a while on your system. So some people, when hearing about Conda, ask, like, what about Pip? You know, Pip is this installation thing that sort of comes with Python, right? And I've seen a lot of confusion about, you know, why would you use Pip versus why would you use Conda? And this is kind of the way that I like to summarize it, is that Pip is a package manager that installs Python packages, only Python packages, within any environment. Conda is a package manager that'll install any package. It'll install C++ or Fortran sources or things like that. But it installs it only within Conda environments. So it's depending on what you want to do, one tool might be better for the workflow or another. But generally, for a data scientist kind of working with data, wanting to use Python to write code and analyze data, I think Conda is the way that I would recommend. Okay, so you have the things installed. Now you need a coding environment. I recommend, these days, I recommend your coding environment be Jupyter Lab. Jupyter Lab is about, what is it, a year and a half old now? I think the 1.0 release is due within the next couple weeks. So it's a relatively new tool, but it's getting to the point of being pretty mature. And what Jupyter Lab is if you install it and then run this Jupyter Lab command, what it does is start up a server on your computer, and then it pops open a web browser, and that web browser lets you kind of have an interface within your web browser to write code and to see outputs and to compose these notebook documents and things like this. So you can click on a launcher, you can get Python 3, and you have a notebook available to you, and you can start running code and seeing the results in line. And the cool things about this notebook document is this .ipynb thing is it's an open document format that you can save and you can share, and then other people can open this up and not only see the results of your code, but they can see the code itself as well. So it's a good way to kind of explore and share the full analysis that you do, rather than just, say, generating a PDF where the reader looks at it and has no idea what went into it. So I started using notebooks about 6 years ago in my research and in my writing, and notebooks have been really instrumental in being able to kind of share technical analyses with colleagues and with other people, and even things like writing blog posts or even writing books for the world to read. The other cool thing about Jupyter Lab, if you've not used that in comparison to Jupyter Notebook, Jupyter Lab contains Jupyter Notebook as kind of, you can think about it as like a little app or a little way of interacting with files within it. But you can also do a lot of other things. You can pop open different windows. You can use code and Markdown, and Jupyter Lab lets you interact with more than just IPyMB things that you can drag in. Look, it's opening an HTML, and you can open another version of the HTML, and then you can actually render things, and you can look at the source. So Jupyter Lab is far more multi-featured than just the notebook itself. It's sort of an umbrella over this notebook thing. So another thing that's in this ecosystem that's been developed in the last maybe year or two that's really interesting is this Binder project. So what Binder does is the Binder team sort of recognized that it can be difficult to always get Jupyter and Jupyter Lab spun up on your own computer because there's some installation things and it's hard to do that. Binder lets you give people a link on the internet to a free virtual machine environment that runs Jupyter and is built off your GitHub repository. So if you have a collection of notebooks and data and scripts that live on GitHub, you can go to this Binder page and enter the repository, and it'll generate a link that lets you go and open a binder and start running the code without anything set up on your own computer. So for my book, the Python Data Science Handbook, I have this Launch Binder button. And what that does when you click it is it pops open, after a little bit of setup, it pops open this Jupyter environment. And this is an actual live code Jupyter environment. So you can go through this book, you can click on the examples, you can run the code, you can modify the code and try it. And it's all running in the cloud. It's not running on your own system. So, if any of you are educators, you can have your students use notebooks and use the Jupyter ecosystem without struggling with the setup on their own machine. And it's gotten, the setup of your own machine has gotten easier over the last few years, but it's still kind of a barrier to entry for a lot of beginning students, especially people who have. Unfortunately, people who have Windows laptops, it can be a little bit difficult to get going on this. So having these cloud-based environments is really cool. Another project that I need to plug, because this is my day job these days, is working on Colab. So Colab is Google's version of kind of a cloud Jupyter notebook environment. And you can think about it as basically Jupyter notebooks on top of Google Drive. So you can run notebooks in the cloud. You go to this collab.research.google.com. You immediately get connected to a virtual machine, and you can save your notebooks in Google Drive, and you can even download them and save them into GitHub. And the cool thing about Jupyter Lab, or about Colab, the reason I'm excited to work on this is because it takes this kind of this open document format from the Jupyter system and connects it to free computing resources, and including powerful hardware like GPUs and TPUs. You can go there and find tutorials on how to use GPUs or TPUs. These are graphical processing units and tensor processing units that can do deep learning type computations really, really quickly. And the cool thing about this is it means that someone from a place who may not have access to that sort of powerful hardware can get online and can try these things out and can teach themselves deep learning without needing to buy a $10,000 compute system to run things locally. So I'm really excited that we get to work on this and kind of provide these resources to use Jupyter Lab, or to use Jupyter notebooks in the cloud without any setup locally. OK, so that's the compute environment. Now, what do you do once you're in there if you want to start working with data? Numpy is the first system that comes to mind. So what Numpy is it's short for numerical Python. And it's basically any time that you're using arrays of data within Python, Numpy is what you're using. Whether you're using SciPy or Scikit-Learn or Pandas or any of these other tools, they're almost always built on top of Numpy because it's this low-level system that lets all the tools talk to each other. And Numpy is really interesting. If you're coming from a background of another language, often the way to use Numpy most effectively is a little different than you're used to. The Numpy generally works through this idea called broadcasting, where basically instead of when you have an array of data like these 10 points right here, you print it up 0 through 9. If you want to operate on all the values in that data, instead of looping through and individually doing mathematical operations on each value, you just treat the array itself as a number. So we say x times 2 plus 1. Sorry, this is too low for this screen. But if you do that, these sort of operations are applied element-wise. So it means that you can very quickly express something like adding two arrays together, or adding a value to every, or adding a number to every value in the array. You don't have to write out the for loop, and it also is much more efficient here. Numpy has other things built in, like the linear algebra tools and Fourier transform type tools that underlie a lot of the algorithms that you're using in machine learning or in deep learning or other aspects of data science. So for example, here's how you compute a singular value decomposition of a matrix. And singular value decomposition is it's a linear algebraic operation on a matrix that underpins a lot of the machine learning models that you use, from things like PCA to even different regression routines. And you can do things like the fast Fourier transform just with the FFT package, and you get out the fast Fourier transform of an array. And the cool thing here is that what's going on under the hood here, remember I talked about how Travis said when he created Numpy, he used to be kind of calling out to all these different routines. What Numpy is doing here is it's actually calling out some very efficient Fortran libraries to do things like the FFT and the SVD. It used to be 20 years ago that you had to compile that Fortran and figure out how to get the data into the Fortran code and then get the result and then get that into MATLAB to plot it. And now this is all in one place. This is all wrapped together in a nice set of Python tools. So it's this is what's really made the Python space workable. So I talked about vectorization. Remember I said if you want to go through, if you're used to programming in C or Fortran or one of these low-level languages, you might think, well, if I want to loop through this array and say multiply it by 2 and add 1, I need to do this for loop and all of this. And it turns out that this is really slow in Python for various reasons if you do this kind of looping. This took 6.4 seconds to loop over 10 million values, which is really slow. You know, our computer chips are measured in in gigahertz now. It shouldn't take 6 seconds to do 10 million values. But if you do this vectorization thing, what it's doing is pushing that for loop down into the compiled layer, and instead of 6 seconds, it's taking 58 milliseconds to do that same operation over 10 million values. So not only is it much easier code to read, it ends up being much faster. So if you're interested in kind of digging into that, like writing these kinds of algorithms in NumPy, the important thing here is getting used to these kinds of vectorized operations. And I have a talk I gave at PyCon a little while ago called Losing Your Loops, and I sort of dig into all the ways that you can use vectorization and these sort of things to speed up code inside NumPy. So I'd encourage you to check that out if you're interested. So NumPy is nice, but it's dense arrays of data, and in the real world, we often have very heterogeneous labeled data, right? Often there are missing values, or we have string labels for columns, or we have different types. And Pandas is the package that's built on top of NumPy that essentially lets you do this sort of operation very, very fast and very efficiently. So Pandas, the main object in Pandas is this data frame object, and you can think of a data frame as like a table, a labeled table of values. So for example, if we have x is 1, 2, 3, y is 4, 5, 6, we print the data frame and we see this index is generated in the x column and the y column. And now we can start, in Pandas, we can start referring to the columns of the data by their name rather than by their index, which makes it much easier to kind of keep track of what you're doing. You don't have to remember that x was the 0th column and y was the 1th column, right? You actually just refer to them by name. And under the hood, what Pandas is doing is it's using NumPy arrays to do that sort of efficient vectorized operation we were talking about, and then organizing the data in a way that's much more human readable into these labeled tables. The other thing that Pandas is excellent for is reading data from disk. If you've ever tried to just use NumPy directly to do something like read a CSV, it can be a little bit painful because NumPy doesn't have all the levels of abstraction that you need to account for what can be in a CSV file. So Pandas lets you do this, and you just do read CSV, and I'd say 90% of the time it just works. It's really nice. And so you get out the data. The other thing that Pandas provides is relational algebra operations, things like group by and aggregations. And so, for example, if you have some columns where this is A1, B2, A3, B4, if you want to group by the ID and then sum the values, you can do this by calling a group by on the column label and then calling sum, and you get that the sum, wow, this is really low, I'm sorry about this. The sum of the A values is 4 and the sum of the B values is 6. So Pandas does these sorts of operations very, very efficiently, which is nice. Okay, so you have your data that you've worked with. Now you want to visualize some things. The kind of the classic tool that I've mentioned already is Matplotlib. And Matplotlib is great. It's a total powerhouse. Over the course of my graduate career and academic career, every paper that I published used Matplotlib exclusively for all the figures, and I think that's true of a lot of people working in the data science space now. So you can conda install Matplotlib, and then you can start plotting things. And Matplotlib, it was designed to look almost identical to MATLAB. Remember when John Hunter was developing it, he was trying to develop an open replacement for MATLAB. So if you ever wonder, why does Matplotlib do things a certain way? Why is its syntax this way? It's because it was trying to replace MATLAB and inherited those API conventions. So the interesting thing, though, is that some of these other tools are built on top of Matplotlib, or built to work with Matplotlib. So for example, in Pandas, if you have a CSV file, or sorry, if you have a data frame that you've created, you don't actually have to go and call these plt.plot type functions anymore. Pandas knows about Matplotlib, and so if you just call the dataframe.plot.scatter, and then give it the columns that you want to plot, you get out this Matplotlib plot that way. So it's sort of like, by combining these tools together and making them aware of each other, things are much cleaner and much more expressive. So building on top of that, there are a couple libraries out there that do this interesting thing of like building a brand new API using matplotlib as the low-level library. And the most famous of these is the one called Seaborn. And what Seaborn is it's a statistical visualization library. So it tries to wrap up all the kinds of statistical visualization models that you'd want to do into simple API calls. So for example, if you do seaborn.pairplot on this data frame, you get a multi-panel facet of all the values against each other. So this is a great way, if you have data sets that are multi-dimensional, like 4 or 5 dimensions, this is a great way to get a feel for how everything relates together. And does anyone recognize this data set, the IRIS data set? It comes up a lot in kind of tutorials and training materials. So yeah, you can explore data that way. Another tool that's really interesting that's come out in the last couple of years that also takes this model of building a new API on top of matplotlib is Plot9. If any of you are coming from the R world and like ggplot, Plot9 is basically trying to bring ggplot style functionality into Python on top of matplotlib. So you have this familiar ggplot syntax of geometries and aesthetics and statistical models, and you can output them on matplotlib. And Plot9's it's really nice to work with. It's not, it doesn't exactly duplicate the experience of being in an R world, but it sort of scratches that itch if you're an R person who misses ggplot in Python. There are other tools out there that are at various have various strengths and weaknesses. If you want to do interactive plotting, there's this tool called Bokeh that's been developed by the same people who developed Anaconda. And what Bokeh does is it allows you to generate these very nice interactive graphics that render in your browser, and you can zoom and pan around. And if you look at the whole Bokeh website, there's a ton of very, very complicated examples that you can do with Bokeh. Another tool that I want to talk about real briefly is Altair. This has kind of been my pet project for the last couple of years. This is a declarative visualization library for Python. Sort of the idea here was to do a grammar-based approach to graphics, similar to the way that ggplot uses a grammar-based approach to plotting, but build it directly into kind of a web-based visualization or a web-based rendering that allows you to build in interactivity. So just with a very kind of concise declarative API, you can create these plots and create these interactive visualizations. And the cool thing about Altair is that the way that the grammar is built makes it very easy to put together multi-panel plots that all respond to each other and build dashboards kind of from scratch. So yeah, if you want to check it out, I gave a tutorial at PyCon last year that's online. You can go to the Altair tutorial, and there's videos there and other materials. And I'd be happy to answer more questions about that. But yeah, Altair has been a pretty fun project. It's been in my transition to kind of industry software engineering. Altair has been my toehold back into the open source world, where I'm doing a lot of contribution there. So. That's fun. And if you kind of want to make sense of all of this, there's this really interesting website that James Bednar put together called PyViz. And basically, he's trying to take all these things that are available in the visualization world in Python and organize them in a way so that people can figure out where to start in terms of visualization. He's related to the Bokeh team, so this website leans a little bit heavily towards the Bokeh ecosystem, but it's a really great resource to see what's out there in the Python data visualization world. Okay, so you've visualized data. You have your environment, you're using Pandas and Numpy, you're visualizing data. Now you want to do some kind of hardcore computation on data. The place to start is SciPy. And SciPy is essentially what it is a tool. It started out as a tool that took all these netlib Fortran libraries that scientists were using to do high-powered computation on slow computers and wraps them in Python so that you don't have to compile the Fortran yourself. and you don't have to think about how to get things in the different formats between the tools. So all these different packages do different scientific routines that you might need in the course of your work, and you can do things really quickly and really interestingly. So for example, here's a model where I took a grid between 0 and 10, calculated the first-order Bessel function, and asked to find the minimum of the first-order Bessel function on that grid, and then plot the result and plot the optimization in red, and you can see that SciPy found this minimum. So these are my microphone's falling off. These are the kind of routines that underlie all the machine learning models that you use. Things like minimization, optimization, special functions, stuff like that. And so SciPy is kind of a great set of low-level routines to build libraries like Scikit-Learn. Oh, Scikit-Learn, there it is. So Scikit-Learn is, if you want to take these SciPy tools and express machine learning models in a very simple API. What Scikit-Learn lets you do is take data like this. So here's a noisy curve of x versus y data. And you can do things like compute a random forest regression that lets you kind of predict the model between the x and the y data right there. And the real key with Scikit-Learn is that it provides this uniform API where you instantiate a model, then you predict on, let's see. Oh yeah, you instantiate the model, then you fit it on your data, and then you predict on new data, and the result is the prediction based on those inputs. And this API, this instantiate, fit, predict thing is used in every model throughout the Scikit-Learn package. So what that means is if if you're using a random forest regressor and you think, oh, this has a little bit too much model flexibility, I want a smoother curve through my points, you can use a model that has that's a little less flexible, that's a little more parametric, and all you have to do is change the model, and you get a different curve. You don't have to change the rest of this code here. See, if we switch back and forth, the bulk of the code is the same. It's just that the model has changed. And that uniform API that Scikit-Learn introduced is what makes it a really nice package for machine learning. You don't have to remember different ways to call different models. It's all kind of the same approach. Okay, so Scikit-Learn, that's interesting. All of this stuff so far has been computation that's in core on one machine. What if you want to start parallelizing your operations? Well, there's this package called Dask that came out a few years ago that also grew out of the Anaconda group, and now has developed a little bit independently. What Dask is it's a lightweight tool to take the types of expressions that you're used to writing in Pandas and Numpy and automatically farm those out to multiple machines or multiple cores or multiple threads or multiple processes. And the nice thing about Dask is it's really intuitive. If you're used to writing NumPy code, where we create a random array, multiply it by 4, take the minimum and print the value, if you're using Dask, all you have to do is the same thing. You multiply your array by 4, you create a Dask array from your original array. You multiply by 4, you take the min, and you print the value. But instead of the value, what you get out is this Dask graph object. And so what is that object? What that graph is it's abstracted away this calculation that you did and said, if I want to multiply a value by 4, take the minimum and print it out, how can I compute that on multiple cores? And it creates this graph where you basically partition your data into 5 chunks, and then each chunk is multiplied by 4, and then you can take the minimum of that chunk and then sort of combine them together and then take the minimum of minimums, and you end up with the same result, right? You don't need that. That's a computation that you can do in multiple parts in parallel. And so if you if you compute the result, you get the same thing that we did before, except it's computed in this parallel system. So this is really powerful, and there's this whole ecosystem of tools developing around Dask to let you do scalable and distributed machine learning type models. And so I would encourage you to check that out if you're interested in kind of taking your PyData computations beyond a single core. A final one that I want to mention, this is an interesting project called Numba. And what Numba is it's trying to take this, this problem with Python that loops are very slow and fix that by compiling Python into fast LLVM bytecode. So here's a typical kind of like function that you see in these sorts of demos, a Fibonacci number generator where you loop through up to n and you generate the Fibonacci numbers and you print the result. And if you try to do this in Python straight up, get the 10,000th Fibonacci number, it's a lot of cycles, and you end up taking, this takes about 2 milliseconds, which is pretty slow as things go for this sort of operation. With Numba, all you have to do is add a decorator on top of here, numba.jit. And this stands for just-in-time compile. And it compiles this function. You don't have to change anything else. You're compiling the function, and the result is that it takes 6 microseconds. So it's a factor of 500 speed up just by adding this little decorator. So these sorts of approaches to speeding up kind of the weakness of Python's interpreted nature are really interesting. And there's also been some cool packages developed in the Numba world to do sophisticated analyses very quickly. And I should mention the Bokeh project. Some of the tools in the Bokeh universe use Numba to speed up the operations that are taking place underneath it. So it's a cool thing. Okay, and finally, the thing I want to mention for speeding up code optimization is Cython. And Cython is this weird hybrid between Python and C, and it's actually one of the most fun languages to code in my opinion. If you take this same Fibonacci Python code, what Cython lets you do is compile this code into C, and then call the result in Python. So here we have this. This takes 2.7 milliseconds again. When you compile this into Cython, it takes 2.4 milliseconds. Yeah. It's a 10% speed up. But the real issue here is that Cython, to really speed things up, needs to know type information. So if you start adding a few little things that say, OK, this a value is an integer, this n value is an integer, and then you do the same thing, you get that same 500x speed up of Numba. But basically, let me flip back and forth. The difference between these is literally just type information on the n and the a and b, and you get that 500x speed up. And Cython is very cool because it underlies. It's this tool that underlies basically everything else that you're using. If you dig into Numpy and SciPy and Pandas and Scikit-Learn and all these other ones, you'll see that at the core they are all using Cython to get the kind of fast data analysis performance that you're used to. And so it's a fun tool to learn, and it really enables a lot of good work in other packages. So I'm just about out of time now. I wanted to leave you with this thought. Python is not a data science language. It's this teaching language. It's this very clean syntax that has accrued data science tools over the course of 2.5 decades. But that's put us in a really interesting place as a PyData community. We have a ton of options, a ton of things that we can pull out of our little pocket knife and do. And making sense of it is a little bit difficult at times, but if you kind of keep in mind the core fundamentals, those core packages, and go from there and look out into the world of what people have done with them, you can do a lot of things with Python. And I really think that Python's sort of general purpose nature is one of its greatest strengths in terms of a language, because it means that instead of using all these disparate tools, switching from Bash to C++ to MATLAB to Mathematica, you can be all in one place, and you can kind of do an end-to-end pipeline in this one language with all these open tools that the community is developing. So I want to leave you with that. 90s, the scripting era, the 2000s, the SciPy era, 2010s, the PyData era, and 2020s. I'm excited to see what's coming, and it's up to all the folks in this room to know what sort of tools and what sort of processes are going to come out next. So thanks very much. This is my contact information if you want to get in touch, and I appreciate you having me here. Thanks. So we have just a couple minutes for questions, if anyone has them. Are the microphones around out there? Yeah. So.
Hi, nice talk. Thank you for that.
Yeah.
My question is, you mentioned you work with Google Colab, and it's a really nice tool, and it's incredible to have it for free. But why is it free? Like, please keep it that way, because I use it for a lot of things. But why is it free?
Yeah, so Colab is a tool that's developed within Google Research. And basically the reason it's free is because the mission of the group is to make those sort of computational resources available. And it can support things, the rest of Google can do things like tutorials on things like TensorFlow, and Colab is a platform for that. So the fact that it's within Google Research and sort of a community service that way is what keeps it free.